how can we use convolution to our advantage? Well, in order to use its full potential, we need to understand fully what mathematical properties convolution has. Hi everyone, this is Jan Wilczek from thewolfsound.com, and today we're going to look at 3 specific properties of convolution which will help us to understand better the operation of filtering. But first, let's recap what convolution is. As we said in the previous video, we have discrete convolution and continuous convolution. Both of them are considering functions which are actually time signals. Now, out of these definitions, we can directly derive various properties of convolution. But today we're going to focus on 3 of them. Each of the proofs is given in the article, which I link to in the description down below. So I highly encourage you to check it out. I believe it does not make sense to include them in the video, but please read through them fully in the article. Okay, let's begin with the properties. The first one is commutativity. It means that we can arbitrarily flip the order of the operation of convolutions being applied. So x star h is equal to h star x. Coming back to our signal and filter example, where h is the impulse response of a filter and x is the input signal to that filter, it turns out that the output of the filter, so the convolution between x and h, can be seen not only as signal x being filtered by h, but also as h being filtered by x. It's kind of weird to look at convolution in this way, but it may be beneficial. Another important interpretation of commutativity is that it makes the ordering of filters in a series irrelevant. So we can freely change the application order of the filters, but the end result will stay the same. The second property we're going to look at is associativity. It means that we can split the convolution with regard to a sum. Well, let's look at its use in filters. If we have a superposition of 2 filtered signals, we can sum the impulse responses of the filters and convolve them only once to get the same output signal. You can imagine the possible optimization opportunities for such a case. The third and last property I wanted to mention is the linearity, which we regard as a combination of distributivity and the associativity with the multiplication operation. It means basically that it does not matter whether we scale the signal before filtering or after, the result will be the same. And also that having a sum of signals filtered together is equal to filtering these signals with the same filter and only then summing them up. If we want to sum these signals eventually, then it may be beneficial to sum them beforehand and then filter them only once. Okay, so these were the 3 properties of convolution which come directly from the definition of convolution, be it in discrete or continuous domain, that I wanted to show you. And please take a look at their proofs in the article which I'll link to down below. It's really interesting to see where these things come from so that we can use their full potential when we're talking about filters. That was all from me today. I'm Jan Wilczek from thewolfsound.com, and if you enjoyed this video, please subscribe, hit the thumbs up, and definitely comment on what you would like to see when it comes to convolution. Other than that, it's all from my side. Take care.